The first issue of this problem is to prove that the integers modulo 5 with a multiplication modulo 5 is not a group. However, if we subtract 0, it becomes a group, right, with respect to multiplication. And the second question that is related to this problem is, if you have this general set, so integers modulo n, with an arbitrary natural number, well, of course, it should be larger than 1, right? And you suppress 0, for which values of n this is a group. Because in the previous exercise, we've seen that this set, even if we suppress 0, is not a group. It's not a group with multiplication, right? Okay? So there are numbers like this one, because that's what we need to prove now. There are numbers for which this is a group and numbers for which this is not a group, right? And we have to distinguish which one and explain why. Okay, let's go first with this. First, multiplication is an associative operation, right? So this is associative. And of course it's commutative, right? So you got both. Commutative. So whatever this is abelian, right? There is a neutral element, right? The neutral element is the 1. Okay, if you multiply any number here, right, by 1, right, times 1, this is, of course, n modulo 5, right? So there's a neutral. However, what fails is the third property, which is the existence of an inverse, because the inverse of 0 does not exist. Does not exist. All right, so z over 5z is an abelian monoid. Abelian monoid with respect to multiplication. Okay, right, but that's the second part is, okay, suppress the 0, right? So remove this 0 here. And what about the rest? Is the rest a group with respect to multiplication? That's the question, right? Okay, well, we just have to check whether every element has an inverse. So the elements of this set are 1, 2, 3, and 4. Well, remember, these are classes modulo 5, right? Okay. So we have just 4 elements here. Of course, 1 is the neutral, so 1 is invertible. Actually, 1 times 1 is equal to 1 modulo 5. It's okay, right? What about 2? Well, 2 by 3 is 6, which is 1 modulo 5. So 3 is the inverse of 2, and of course 2 is the inverse of 3. So these two elements are invertible. And about 4, if you square 4, so multiply 4 by 4, you get 16, and 16 is 1 modulo 5. So 4 is its own inverse. So it's got an inverse as well. So every element has an inverse. So this is a group, it's an abelian group. With respect to multiplication. Okay? Right. And now here comes the big question. Suppose that you have now this set, right? So these are all the integers modulo n, where n is arbitrary, and you remove this 0. You still consider multiplication. For which values of n this is a group? Well, the question is the following. You have to take any arbitrary element a from this set, right? So it is any number between 1 and n, and n minus 1, sorry. Okay, you take any element there, and then you have to find an element x such that a multiplied by x gives you 1 modulo n. All right, but this is a congruence, and we know when this congruence can be solved. And the condition for this to be solved is that the greatest common divisor of a and n, let me just write GCD, greatest common divisor of these two numbers, has to be 1. And that must happen for every number a, for every a, 1, 2, 3, up to n minus 1. So that must be true for every every one of these numbers here. And that is only possible if n is a prime number. So that's the condition for this to be a group. So only these sets, right, minus 0, with respect to the product, where P is a prime, these are abelian groups, right? If P is not a prime, then this is just a monoid, because there are elements which lack the inverse. And one case we saw is the case where P is equal to 6, right? Which is not a prime, and this is not a group, because there are elements like 2 which do not have an inverse.